All right, well, hello everyone, and welcome to week 2 of linear algebra. Today we'll be talking about systems of linear equations. Um, this is picking up after we finished talking about vectors. So, systems of linear equations. Today's video will be just an introduction. What are systems of linear equations? I've drawn this awesome diagram. Well, I think it's awesome. Um, which kind of represents that there are three major interpretations or ways of looking at a system of equations. The most common one is this guy, where we just have a list of equations, and that's the one that we're going to talk the most about today. Um, Another way of thinking about it is on the side here we have just a little graph. Now notice I have two linear equations in two variables. It's like slope, standard form of a line, right? Well, if it's a line, we can graph it, and if we can graph it, we can find the solutions to that equation there and plot them as points, right? That's what it is to graph a line. And then notice there's like a conspicuous point of intersection that we might be interested in, right? And then there's a third interpretation where it's like we're asking what linear combination of these two vectors, 2, 1, and 1, -3, gives us this third vector, 8, -3. We're trying to solve for what linear combination does that, okay? That is something that we're not going to focus on today. Today we're going to mainly talk about the other two. I want to start by giving a definition, like what is a linear equation. Now, a linear equation is something that we're familiar with when it comes to two variables. So specifically the equation of a line. You might recognize ax plus by equals c is the equation of a line this is a line in R2, right? Well, this is pretty straightforward. Oh, we call it in standard form, yeah? You may have also seen, especially if you've taken or are planning to take Calc 3, you may have seen the equation of a plane in R3. So this is ax plus by plus cz equals d. This is a plane in R3. Okay, let's dial. So these are the two most common, most familiar expressions of just a single linear equation. We've actually seen another one. Ax equals b. This is boring because it's really just asking, x equals b over a. In other words, this is just a point on the number line. Okay. However, okay, so this is not a really fun example, just a point on a number line. But notice there's a very, very clear pattern that pops out when we just allow for that case. All we're doing to increase is like increasing the number of variables, one for the dimension, for each dimension of space that we're considering, and then we're just carving out a single equation by taking a linear combination of those variables, setting it equal to a constant. Just in case you guys are interested, let me show you the equation for a hyperplane. By the way, after plane, hyperplane is a catch-all term where it basically is just saying, 4 or more. So if I did ax1 plus bx2 plus cx3 plus dx4 equals e, for example. Okay, this is what's called a three-plane. in R4. Don't ask me to visualize it for you. I mean, the three-plane is not so bad. It's just imagine three-dimensional space. But living inside of four-dimensional space, I have no idea. I've got nothing. For those of you who are really into physics, you could imagine this as a three-dimensional snapshot of four-dimensional space-time. So a freeze frame of the universe, if you'd like. But I don't much prefer the mathematical interpretation where it's just a linear combination of four independent variables. Okay, great. So that leads us, but notice that's super easy to generalize, right? And so we can just write down a definition. So a linear equation in n variables, or we'll say in the n variables, x1, x2, we'll just write them out, all the way up to xn, is an equation of the form and then we just do what we did before. A1 x1 plus a2 x2 all the way up to plus an xn equals b, where the ai's are called coefficients, and b is called the constant. So we call b the constant, the ai's are the coefficients, and this is a linear equation in n variables. Okay, and notice it just, all we did was take the pattern and make it n variables long. Okay, and yeah, this sweeps out a n minus one hyperplane inside of n dimensional space, whatever that means. Okay, great. But like, let's look at some examples of linear equations. For example, 3x plus 2y equals 7, or pi x plus ey minus the square root of 2z equals negative 12. I mean, that's a horrendous linear equation. But notice, look, pi is a real number, e is a real number, negative root 2, real number, terrible number, but whatever, right? Now, okay, and so on, right? Let me show you a non-example, though, or a couple non-examples. 3x squared plus 2 over y, 2 times 1 over y, equals 7. Notice both of the variables are causing something to break, right? We're not allowed to take powers of our variable. We're also not allowed to put the variable in the denominator, nothing like that. Let's do another one. Pi x plus ey minus root 2z equals negative 12. Oh, wait, it's the same as the other one. No, look. There's a root, yeah, we can't take the square root of a variable, right? If any of this breaks, it is not a linear equation. All we're allowed to do is take the variables, multiply them by coefficients, and add them together. No square roots, no sine functions, no exponents, no, nothing like that. Okay. In other words, we keep it boring. No, we keep it simple. Good. Okay, so if we know now we know what a system of linear equations is. Let's we know what a single linear equation is. Let's talk about a system of linear equations. Okay, now a system essentially all we do is okay, a system of linear equations. I'll tell you the definition. Um, okay, you're going to be very underwhelmed by this. A system of linear equations is a finite list of linear equations. Okay? Each with this we will say each with the same variables. So okay. Um a solution to a system, I will say to a linear system. Now, let me before I finish the definition, let me just say what I mean by that. A linear system is just another way of saying system of linear equations. Sometimes we just don't have the endurance to say the whole phrase system of linear equations, and so we just say linear system. Okay, so when don't be confused when you hear, oh wait, what is a linear system? Is that different from a system of linear equations? No, they're the same. Okay. So a solution to a linear system is a vector whose components satisfy all equations in the system simultaneously. So, like in other words, if I had a linear system with two equations in it, I can't just pull a vector whose components satisfy one of the equations and another vector whose components satisfy another equation, and just call that pair of vectors a solution. No, no, nothing like that. We need one vector that satisfies all of the equations at the same time. Okay? Only then does it deserve the name solution to the system of linear equations, right? So, and then of course, okay, this next definition is not very enlightening, but the solution set for a system, okay, is the set of vectors that is a set of solutions. Why is this even a definition? Okay. Okay. For what it's worth, it is worth pointing out because we care like in our subject. That's actually what we care about. We care about the solution set. So one individual solution might be interesting, but sometimes there are infinitely many solutions. And so we want to go and find all of those, not just like point to one of them, right? So we're interested actually in the entire set of solutions. So let's look at an example. I want to start with this little guy at the end. So notice we have our system of equations. It's a finite list of two equations. The vector 1, 6, notice that is a solution to the first equation. And by the way, the solution to a linear equation is just a vector whose components satisfy that equation, right? No tricks. That just is what it is what it means to be a solution to a linear equation, right? However, notice if you take, 1, 6 is a solution because, like, look, if you plug in 1 and you plug in 1 for x and 6 for y, right? Well, 2 times 1 plus 6 is indeed 8. That's a true mathematical statement, which means that this vector, 1, 6, is a solution to the first equation. However, go ahead and take 1 and subtract 3 times 6. 1 minus 18 is negative 17. And last I checked, negative 17 is not equal to negative 3. That's a false mathematical statement, which means 1, 6 is not a solution to the second equation. And so 1, 6 is not a solution to the entire system of linear equations because it has to satisfy all equations simultaneously. Now, if we play that game with the vector 3, 2, 3 times 2 is 6, plus 2 is 8. So that's good. 3, 2 is a solution to the first equation. And 3 minus 6 is negative 3, which means that 3, 2 is a solution to the second equation. Okay, good. Good. So 3, 2 is a solution to the entire system of linear equations. It is a member of the solution set. As it turns out, it is the only member of this is the entire solution set for the system of linear equations. However, I'm not going to tell you how I know that. And by the way, I made up this example. You won't find it in the book. This is I guess this is the very first example in the book, but they don't have the solution. So, but how do we know it's the only one? We'll get there. Probably in the next section. Okay. Now, for now, like I said, we are interested in possibles in the solution sets. So I want to just take a moment to talk about what are the possibilities for a solution set. So we have two types of systems of linear equations. A system can either be consistent or inconsistent. This just means inconsistent. Okay, so I'll just tell you what inconsistent is. The solution set is empty. Let me write down some linear equations that, when taken as a system of linear equations, is inconsistent. X plus y equals 2, and x plus y equals 3. Okay, now my challenge to you is find me two real numbers whose sum is 2 and 3. That's quite the contradiction. One way you can see that is if you just subtract these two equations. You're asking me to find two numbers such that 0 is equal to negative 1. Never is the answer for that. So the system is inconsistent, right? Consistent. There is at least one solution. There's at least one solution to the system of linear equations. Okay, so that's not terribly helpful. Um, we can actually get a little bit more nuanced than this. There are three possible solution set sizes, we'll say. And it's strange, just by the nature of how systems of equations work, you could have a system that has, for example, no solutions, right? We saw one already. No solutions. Like zero solutions. And this would be an inconsistent system. But you could also have one solution, like a unique solution, which is actually the example that we saw previously. One unique. And then this would be the case where it's like, oh, this is a consistent. I mean, hey, at least one solution that counts. So this is consistent. And then, like, what if you had two solutions? What if you were able to find two solutions to a system of linear equations? Well, as it turns out, any linear combination of those solutions will also be a solution. Which means already I can have infinitely many solutions just by taking any multiple of any of. Well, okay, no, we'll just we'll say that the last possible option is infinitely many. Okay, this is consistent as well. I want to take a moment to just draw some pictures, some little doodles. So we'll just zoom in over here. Great having an iPad that I can do this. So if I wanted an inconsistent system, remember we're talking about a system of linear equations. Let's work in R2. Okay, I want to write down two lines. Oh, if you haven't noticed by now, the vector, which is a solution to a system of linear equations, is the intersection point of those lines, or an intersection point of two planes. Two planes will intersect along a line, right? I've drawn this picture a few times, I think. Something like this. Two planes will intersect along a line. What is that? Okay, I don't know. Anyway. So I want to write down two lines in R2 which do not intersect. They better be parallel. There you go. Actually, let me write down the two that we saw already. X plus y equals 2, and x plus y equals 3. More or less, right? Y equals negative x plus 2 or whatever. Okay, if I wanted to do a consistent system with one unique solution, this is going to be the most common case. Just draw two lines. They'll have a unique intersection point, right? And if I wanted a consistent system with infinitely many solutions in R2, I need to draw two lines which intersect at infinitely many points. That's still not too hard to do. Just draw the same line twice. I mean, it's kind of silly to do such a thing, but this will come up. You'll be amazed how often you have infinitely many solutions. Okay, that's enough of that. And now I do have one last definition that's going to lead us into the very last thing that we'll talk about. So how do you know when two systems are equivalent? Well, we just define equivalence between linear systems as in terms of the solution sets. If they have the same solution set, then they are equivalent linear systems. So here are two, x plus y equals 4 and x minus y equals 6. And then we have x plus y equals 4 and x equals 5. Now, The solution in both cases is x equals, of course, 5, and y equals -1. Thanks. Okay, you can see that by, in the second case, like x has to be equal to 5. But if x is 5, how do you solve the first equation? You have to take a number, add it to 5, and get 4. You only have one option, right? So, but let me also draw these for you so that you know that we're looking at two different linear systems. In the first case, we're looking at x plus y equals 4, and x minus y equals 6. It's a little bit higher up. Okay, that's good enough. And there's your point. 5, -1. Oh, wait, what have I done? I've done this wrong. Oh, sorry. X minus y, I drew y minus x. X, okay. Y equals x minus 6. So like this. Okay, whatever. And there's your 5, -1. Okay. In the second case, the same first line, but now we just do x equals 5, the vertical line. And you have the same spot. We could even have drawn them on the same grid or same Cartesian plane. But it's kind of confusing because they're two separate linear systems, right? But they're equivalent because they have the same solution set. Anyway, great. Okay, so why would we care about equivalence between linear systems? It's because we have to learn how to solve them. This is one of the main points of our class. We need to be able to solve linear systems, and so we're going to spend a lot of time learning how to solve linear systems. It just is what it is. Okay, so the strategy is two parts. First, we're going to find an equivalent system that's easier to solve. And then step two, we're going to use back substitution. And now, before I show you what this example is, remember when you were like learning how to solve a single linear equation? Like, remember those two-step equations from a long time ago? If it was like 3x plus 4 equals 7. And what do you do? Oh, nice. That's going to be nice. You have to like, okay, yes, I could ask what number do I triple and then add 4 to in order to get 7? And I might just be able to conjure the number 1. But I also could have done it like this. Just find an equivalent linear equation by subtracting 4 from both sides. 3x equals 3. And then I might ask, what number do I have to triple in order to get to the number 3? And maybe I'm just having a bad day. I don't know. And I just have to find an even more easier equivalent system. So I'll just divide both sides by 3. So x equals 1. And now I'm like, okay, what number is equal to 1? Okay. Well, yeah, anyway. We've done this before. So in other words, we're going to find some steps that are going to make a linear system easier to solve. Okay. Now, in this example, the system has already been put into a form that's easy to do back substitution on. So we're not going to spend too much time on. We're gonna do step 1 afterward. First, we'll show how the back substitution works. So the first thing we have to do, look at this easiest equation. If 2z is equal to 4, by the way, this is a system of three equations in three variables. This is three planes that are all simultaneously intersecting in three-dimensional space, two planes in three space. So something like, a plane and then another plane, they meet along some line. You know what I'm talking about? Right? And then there'll be a third plane that slices through, and maybe, so we expect one point of intersection. This is a terrible picture, sorry. Anyway, when we're asked, in order for a vector to be a solution to the system of linear equations, it has to simultaneously satisfy all three equations. So, this third equation tells us that z, the third component of your vector, must be precisely 2, right? Because 2z equals 4, so z must be equal to 2. Okay, well, in that case, no matter what we're trying to do, z has to be equal to 2. So we can substitute z equals 2 into the second equation. That new equation reads 3y minus 2 equals 7. So 3y equals 9, which tells us that y has to be equal to 3. So z is equal to 2 and y is equal to 3. We can plug both pieces of information into the first equation, which will then read that x minus 2 times 3 plus 2 equals -4. X minus 6 plus 2 equals -4. X equals 0. So if x equals 0, y equals 3, and z equals 2, then the unique solution is 0, 3, 2. Unique solution because at no point did we have any freedom. It's like z was fixed as a sum number. As a consequence, y had to be a fixed number, and as a consequence, x was fixed. We had no choices. Okay, good. So now we're presented with another linear system. This one is significantly more difficult to look at because look, there's no obvious solution. There's no obvious place to start, right? In the previous example, we just had 2z equals 4. It's like, okay, well, you just added an extra step because you just told me what z has to be equal to, right? Oh, you've disguised what z has to be equal to. Well, here there's no clear immediate first step. So what I'm going to show you, so this is part 1 of our strategy, right? We need to convert this linear system into an equivalent system, so something that has the same solution set, but which is easier to solve. Now, the steps I'm going to show you are going to look like they came out of nowhere, and really they're going to be more in the spirit of what we're going to talk about in the next video. But for now, we'll just get after it. So what we do is I've written down a giant bunch of square brackets. This is a matrix. The vertical bar is going to make this into an augmented matrix. Augmented just means it's a matrix with an extra column in it, which has a different meaning than the rest of the matrix. Okay, so no tricks. By the way, so a matrix is a grid of numbers, and it's the word matrix actually comes from the same word as like matriarch, like has like womb connotations, and the idea is that like wrapped up inside the brackets is the meat of, or the the contents of your linear system, right? And so anyway, it's a very interesting root word. And I will also tell you right now, the plural for matrix is matrices. Like I have three matrices, not three matrices. Don't say that. People will look at you and they'll think, who taught you linear algebra? And then I'm going to look bad and then I'm going to be sad. Okay? So, good. Yeah, matrices. But right now, okay, and actually, here's a sentence using it. Right now, what we're going to do is convert to this linear system into an equivalent one by doing operations on these augmented matrices. There you go. So, let's write down, first of all, what goes inside this matrix. It'll be just the coefficients. 1, -2, 1. 2, -4, 4. -1, 5, -2. And then in this column, we put the constants for the the constants for the linear equations. So -4, -4, 11. Okay. Now, what are we going to do? So, if you remember having to do this ever in an algebra class or something like that, you may have remembered words like substitution and elimination, and probably graphing. Well, anyway, we're going to appeal to that elimination strategy. We're going to subtract multiples of the first equation from the other equations, right? And that's a legal thing to do, mathematically speaking. I'm going to look at the first equation. Look, the left-hand side is quote unquote equal to the right-hand side. So if I'm allowed to subtract anything from one side of the equation as long as I subtract an equivalent quantity from the other side of the equation, right? So let's look at the third row. I'm going to subtract x minus 2y plus z from the left and -4 from the right. When I do that, and this is in the third equation. When I do, the linear system becomes the following. X minus 2y plus z equals -4. 2x minus 4y plus 4z equals -4. And then, sorry. What am I doing? When I add, don't add. Don't subtract, add. I said subtract, I meant do the thing that makes these x's cancel, right? Add. 2. Okay. Very important. We want to cancel out some kind of variable, if possible. So the third equation, when I add x and -x, I get 0. When I add -2y and 5y, I get 3y. And when I add z and -2z, I get -z. And on the right-hand side, when I add -4 and +11, I get 7. That was promising. Let's see if we can do something with the second equations. Oh, and by the way, notice we could have done an even faster way if we had just appealed to the augmented matrix. Look, if I just add the first row to the last row, I'll get an augmented matrix. 1, -2, 1, 2, -4, 4. And then when I add 1 and -1, I get 0. When I add -2 and 5, I get 3. And when I add 1 and -2, I get -1. augmented with -4, -4, and then I add -4 and 11, I get 7. Notice I did exactly the same thing to produce this augmented matrix, but it was just more arithmetic and less algebra, right? So this is a little bit faster to use the augmented matrix. So for the next step, we want to try and create the or we'll try to manipulate the second equation. And so what we're going to do is take that first row and subtract this time, honest. Take 2 times the first row and subtract it from the second row. Okay? 2 times it because, again, I want to get the x's to cancel. So -2, +4, -2, and +8 is what 2 times the first row is. We're going to take that and whatever. Yeah. Well, anyway, 2. Let me write it with words. Subtract. Honest. Subtract. 2 times row 1 from row 2. Notice I used some shorthand. And in general, notice every time you introduce a new step, the notation gets shorter, right? That's the idea. We're gonna increase our efficiency. So anyway, subtract 2 times row 1 from row 2. And I'm talking about rows of the matrix, right? So the first row, again, is not changing. 1, -2, 1, -4. The second row, -2 plus 2 is 0. 4 plus -4 is 0 again. -2 plus 4 is 2. And +8 plus -4 is 4. And then the last row hasn't changed. In terms of a linear system, it looks like x minus 2y plus z equals -4. I guess 2z equals +4. And 3y minus z equals 7. Notice this is very similar to the linear system that we were talking about. It's just that the last 2 equations are switched. Well, let's just switch them. Interchange rows 2 and 3. So our system will become 1, -2, 1, -4, 3, -1, 7, 2, 4, 0s everywhere else. And as a linear system, it's x minus 2y plus z equals -4, 2z equals, no. Now we switched, right? 3y minus z equals 7, and 2z equals 4. And so we've already solved this, right? It was 0, 3, 2 is our solution set. Because we already solved this one, right? We would have to go, and now that we've got it in this form, we can now do all the back substituting. Okay, that's all I have for you today. Next time, we'll talk about a more general strategy for solving systems of linear equations. We'll also see what happens when you've got infinitely many solutions and how do you represent final answer in that form. And a bunch of other fun stuff. I will see you in the next video.